Okay, so let's begin. So since the course and lab are going together, I find it very useful for both me and you. Now, I have been going around in the lab talking to the groups, and it seems you are gradually, having a grip on the subject, which is very nice to see. We also had a quiz, the first quiz. Since the quiz was the first one, uh, I see that it has been easy. Yeah, so which is also fine. And we are also quite liberal with the evaluation. So I'll discuss the answers to the questions. Most of you have done very well in the quiz. But of course, going forward, okay, things will be a little more demanding as we move ahead. But doing the lab and the theory together seriously should give you a very strong grip on foundations of AI, which you will be able to use going forward if you get into nitty-gritties of AI and build your career in artificial intelligence, for example. So I'll move forward. And today we will do two very important functions uh, for uh, for deep learning AI, Sigmoid and Softmax. So in the lab, you have been trying to train a sigmoid neuron. Now, sigmoid neuron is sigmoid function, which is 1 by 1 plus e to the power minus x, is a continuous function. Okay. And perceptron training algorithm requires you to know the class of every data point, right? Is it in the 1 class or 0 class? Now, there is no such point of discontinuity for sigmoid. So of course, we have kept as 0.9 as the upper threshold for belonging to one class. If the output of the sigmoid neuron is a value above 0.9, then the class of the point is 1. And if the output falls below 0.1, the output of the class is 0. So with that decision is used for inferencing when the new data points are coming. The training of the sigmoid neuron has to be done through gradient descent. And I've seen, I think 5-6 groups I talked to, you are trying to take the derivative inside the program, inside your Python program. But that's not necessary. In fact, you should not do it. You should use the derivative for gradient descent to arrive at the final weight change expression, which you are going to do in the class. And then use that expression to arrive at the correct weight, which in future will give more than 0.9 for 1 class vectors and less than 0.1 for 0 class vectors. So we have to derive the weight change rule for a sigmoid neuron. Another very important point about sigmoid neuron is that it has a very nice, easily computable derivative, which is output into 1 minus output. Okay. And the output of the sigmoid neuron, since it is between 0 and 1, the output of the sigmoid neuron can be looked upon as a probability value. So here is a mechanism which takes a data instance and gives a probability value. Okay. And output into 1 minus output is interestingly the probability of one class into probability of the other class. Okay, this is also a nice observation. So now you might come back and say that, well, here is a device which takes an input and gives a probability value. Probability value, you consider this to be a probability value. This is between 0 and 1. So it's a probability value, which you might question. Okay, pay attention to this point. Again, please don't use your laptop at this point of time. Pay attention to what I'm saying. So this gives a probability value. How does it relate to our ordinary notion of probability? Okay, most of us are used to a notion of probability, which is a ratio of counts. Okay, which is a ratio of counts. Now, if you toss a coin 100 times and head comes up 65 times, we say the probability of obtaining head is 0.65. And that corresponds to a property of the coin. Okay, property of the coin. We say that the probability of obtaining the head from the coin is 0.65. That corresponds to a property. And it comes from maximum likelihood estimate. Okay, so you have the likelihood of the observation. You differentiate with respect to the parameter, which is the probability of head, equate it to 0, and the probability comes out to be ratio of total number of heads obtained and total number of trials. Okay, so in what sense is this a probability which is coming out from the sigmoid neuron? You can show later that the cross entropy loss from the sigmoid neuron, okay, is equivalent to minimizing the cross entropy loss is equivalent to maximizing the likelihood of the data. Okay, this will prove in the class. And therefore, this builds a bridge between maximum likelihood notion of probability and the neural network notion of probability. Okay, it links these two notions of probability. These kind of linkages are very interesting. One of the most interesting such linkages is bridging the two notions of entropy, one from thermodynamics, the other from information theory. Okay, showing that information theoretic notion of entropy is same as thermodynamic notion of entropy is also a very interesting point. Okay, so the notion of probability, which is maximum likelihood estimate based, and the notion of probability, which comes from cross entropy, linking these two is an important theoretical foundation. So you should be clear about that point. Okay, while you're implementing all these systems, all these theoretical foundations should be clear. Okay, so let's proceed. I'll just say one more time. Do not try to take the derivative inside your program. Okay, the consequence of the derivative is the weight change expression. And in the lab in Thursday's class today, you will use the sigmoid neuron to see what it gives for linearly separable functions and not linearly separable functions. Does one sigmoid neuron compute the XOR function? One sigmoid neuron? Do you have some idea? Can it compute XOR? Why not? Okay, so this can be formally proved by setting up linear inequalities. Okay, 1 class above 0.9, 0 class below 0.1, set up the inequalities, and you will see that it gives rise to an inconsistent set of inequalities. So you need multiple sigmoid neurons and a multi-layer sigmoid network. Okay, in the week 3 of 27 Jan, last week, we covered a very fundamental observation that the threshold functions computable by a perceptron is equal to the number of regions produced by 2 to the power n hyperplanes obtained by plugging in the values x1, x2 up to xn in the equation sigma I equal to 1 to n, wi xi equal to theta. Okay, so these 5-6 slides of what was covered in the last week is useful when you prepare for a quiz or midsem or endsem to quickly see what was emphasized, because what is emphasized by the professor is likely to appear in the question, right? This is what I think important, so they might make an appearance in the questions. But yeah, and in general, exam or not, these are important points. So linking the total number of regions produced by hyperplanes to the capacity of the perceptron is again an important theoretical foundation. Then we set up the recurrence relation for counting the number of hyperplanes. And this recurrence relation is based on the fact that the nth hyperplane, when it comes in, it produces Rn, D regions. So n hyperplanes passing through the origin in the d-dimensional space, it produces Rn, D regions. which is equal to the number of regions produced by n-1 hyperplanes in the same space, plus number of regions produced on the nth hyperplane, which is dimension 1 less, that is d-1, and all the existing hyperplanes intersecting in the on the nth hyperplane. The number of regions produced is Rn-1, d-1. When we solve this recurrence relation with boundary conditions, we get this expression for the number of regions in the d-dimensional space. And the implication of this is that the number of regions produced by produced by 2 to the power m hyperplanes for a perceptron with m inputs, okay, is order of 2m square, 2 to the power m square, which is very, very small compared to 2 to the power m, which is the total number of Boolean functions. Okay, and then we started gradient descent technique with the total sum square error expression. And the weight is m is the destination neuron, n is the source neuron, and the change in weight is proportional to minus delta E delta W mn. This is the guiding equation. And from there, through various derivations for a feed-forward network, we obtain the universal rule of deep neural network training, which is delta WJI is equal to learning rate into delta J, a quantity in the destination neuron, and OI, the output of the source neuron. This delta J value is target minus output into the station derivative of the neuron for an output layer neuron. And for hidden layer neurons, it is backpropagated delta weighted by backward weights into the station derivative of the neuron, okay, which we'll spend more time on. We'll derive this expression also rigorously. So this is the backpropagation rule, and we took up an application for skin disease prediction by a neural network, which had output diseases, which had diseases represented in the output layer as the number of diseases, so the number of neurons, and the total number of symptoms, which are 96 in number, were represented by 96 neurons in the input layer. In the intermediate layer, we had 20 hidden layer neurons, which were obtained by trial and error. The hidden layer neurons tend to aggregate diseases with common symptoms. Okay, so this hidden layer neuron brings in the power of computation. Now, one hidden layer neural network is not at all common these days. The number of layers is very, very large. The number of neurons is also very, very large. And the neural networks which function at the level of human beings have millions, billions of parameters. Okay, but the interesting thing is that the training rule is only one, backpropagation in some form. Okay, any question on what was done in the last week? Remember, you had to derive that RND is indeed equal to this expression. Okay, you also had to derive that for an M input neuron, RND is order 2m square. You had to derive this. Okay, please do that. Okay, now let's understand the sigmoid neuron. For the sigmoid neuron, the inputs are x0, x1 up to xm. The upper suffix I indicates the ith data point. Okay, so for the ith data point, output OI is equal to 1 by 1 plus e to the power minus net I. So you have to mark this particular symbol very carefully. Minus net I is the net input coming into the sigmoid neuron, okay, which is the dot product of the weight vector and the input vector. The bias is absorbed in the weight weight values with a fictitious connection with a input of -1. Okay, as you have implemented for perceptron training algorithm in the lab. So OI is equal to 1 by 1 plus e to the power minus net I. Net I is equal to sigma Wj xj for over all the connections. Now, sigmoid function, it can saturate. Okay, sigmoid function's curve is this. Okay, so it has saturation towards -infinity and saturation towards +infinity. Now, sigmoid neuron has an interesting biological basis, neurophysiological basis, and also an interesting history. How was the sigmoid function thought about by neural scientists, neural engineers, let's say? So this kind of saturation is important for the brain. Otherwise, you can have what is called coronary thrombosis. People in the grip of intense emotion, intense anger, intense joy, intense surprise, run the risk of run two risks, either heart attack or brain attack, which is coronary thrombosis. So what happens in the brain is that in case of intense emotion, lots of neurons fire and they do this furiously. Okay. And unless the brain has this saturation mechanism, this kind of intense firing can get into a vicious positive feedback loop. Okay. And if the curve was exponentially rising, then after some time, there would be a rupture of neurons. Okay. The cell boundaries will break. And this actually happens, many times. Regions of brain get paralyzed because of this intense firing of neurons. So neurons have this behavior of saturation and thereby saving themselves. So this inspiration was taken, and the researchers looked for a function which mimics this kind of biological behavior. And that gave rise to the adoption of sigmoid neuron. Okay. Just like perceptron, the threshold function also was biologically inspired because neurons fire or inhibit. Okay, they are either in 0 state or they fire, go to the 1 state. Okay, so this kind of saturating behavior is actually seen in nature, and therefore there is a nice biological foundation for this. Now the basic sigmoid function is y is equal to 1 by 1 plus e to the power minus x. And a derivative of y with respect to x is y into 1 minus y, which you can easily show. And you can change the shape of the sigmoid neuron. Okay, this shape of the sigmoid neuron. You can increase its slope or decrease it by introducing a k. Okay, here, k here. So as k increases, as k tends to infinity, the sigmoid tends to the step function. Okay, so sigmoid in the limiting case becomes the step function. That could be your argument to say that in the limiting case, sigmoid is like the step function. So since perceptron cannot compute XOR, sigmoid also should not be able to compute XOR. That could be an argument, but a more rigorous argument is through linear inequalities. Okay. So now decision making under sigmoid. The output of the sigmoid is between 0 and 1. We look upon this value as the probability of class 1 arbitrarily. I take one of the classes. Okay, let's say the problem being solved is whether to sanction loan or not. Okay, if the sigmoid output is 0.7, then I say that the probability of sanctioning loan is 0.7, not sanctioning is 0.3. You can do the opposite also. Just be consistent. Okay. If C1 is for the sigmoid output, then C2 must be 1 minus the sigmoid output. So 1 minus sigmoid x is the probability of class 2 C2. Now, this is the decision rule. Decide in favor of C1 if probability of C1 is greater than probability of C2. Okay, probability of C1 is greater than probability of C2. Otherwise, the decision is in favor of C2. Now, since PC2 is 1 minus PC1, this inequality shows that if PC1 is more than 0.5, then C1 is the favorable, C1 receives the favorable decision. Okay, the consequence of PC1 greater than PC2 is PC1 is more than 0.5. Right. So now sigmoid function is used for two-class classification problem. Why can't we use sigmoid for n-class classification? Here is a thinking exercise for you. On the curve for sigmoid, we can mark regions. Okay, let's say 0 to 0.1 is class number 0, 0.1 to 0.2 class number 1, 0.2 to 0.3 class number 2, and so on. Okay, and this way maybe you can have 10, 20, as many number of classes as you want. Will this work? Okay, can such a learning situation work? This is a thinking exercise for you. But normally what is done is that if there are more than 2 classes, then you recruit more neurons in the output layer. Okay, so if there are 3 classes, then 3 neurons. You can do with 2 neurons because 1 neuron will be 1 minus the probability, 1 minus the output of the other 2 neurons. But normally for 3 classes, 3 neurons, n classes, n neurons. Then you need a different function that's called the softmax function. So 2 class to multi-class, let's say there are C classes, then we have to adopt another function called softmax, which is a generalization of the sigmoid neuron. For the ith input, the Cth class, which is small c, C varies over all the classes. In softmax, decide for that class which has the highest probability. This is called the winner-take-all strategy. Okay, the neuron which has the maximum output becomes the winner. The decision is in favor of that particular class corresponding to that neuron. Okay, now what is softmax? It turns a vector of k real values into a vector of k real values that sum to 1. And these k real values are non-negative. Input values can be positive, negative, 0, or greater than 1. But softmax transforms them into values between 0 and 1 so that they can be interpreted as probabilities. The mathematical form of the softmax function is this. Sigma, now sigma is used for both sigmoid and softmax. Okay, you understand this to be softmax or sigmoid from the context. So if sigma operates on a vector of, let's say, n components, then the sigma's output is e to the power zi divided by j equal to 1 to k e to the power zj. And sigma is the softmax function. So let's take an example. Suppose the input vector is 1, 2, 3. They are not between 0 and 1. So z1 is equal to 1, z2 equal to 2, z3 equal to 3. Then e to the power 1 is to 2.72, e to the power 2 is 7.39, e to the power 3 is 20.09. Then sigma z is found in the following way. The first component of the softmax vector is 2.72 divided by sum of e square plus e cube. Okay, this value, which gives rise to 0.09. 7.39 by this quantity, 20.09 by this quantity. So we have the softmax equivalent of 1, 2, 3 as 0.09, 0.24, 0.67. Notice that the softmax function is monotonic. Okay, if the jth component is more than I, then the jth component is more than the I in the softmax output also. Okay, so it preserves the monotonicity. So this is how softmax is computed. I can now look upon this value as a probability distribution because the values sum to 1 and the values are between 0 and 1. Now, softmax and cross entropy are very important for AI because they go hand in hand. We get the output of a machine learning system, a learning system in the softmax, and we compute the distance from the target behavior by the cross entropy function. So let us say we have the softmax vector obtained from an example where the softmax vector is 0.09, 0.24, 0.65. Let's say these values correspond to 3 classes. Let's say in sentiment analysis. Okay, we have a natural language processing system which is deciding if the input text has positive, negative, or neutral sentiment. So positive, negative, and neutral sentiments. So we see that in this particular case, the probability of positive sentiment is about 0.1, negative sentiment is about 0.2, and neutral sentiment is 0.7. So most probably, the input text has neutral sentiment. It's neither positive nor negative. Now you might come back and say, so here are the examples. I like the story of the movie. This has positive sentiment. However, the acting is weak. This is negative sentiment. The protagonist, that is the hero, is a sports coach. So this is a neutral sentiment. It doesn't have any positive or negative sentiment. Now I might come back and say that, well, I don't see the need for any probability here. I can look at as a human being, I look at the sentence and immediately decide whether it is positive or negative sentiment or not. Okay, the whole point is that you have lots of world knowledge. Okay, so you have lots of world knowledge which you have acquired through years of education, life experiences. The deep learning system does not have that world knowledge. The AI system doesn't have that world knowledge. It has only data. So it necessarily is limited by the training data. The other point that even human beings can be confused many times. Okay, because it depends on the context. I like the storyline of the movie could be a sarcastic statement. Okay, it depends on the body language. Yeah, I like the storyline of the movie. This is not a very positive expression. Some kind of sarcastic expression. That is, so this sentence has negative emotion. So detecting that is non-trivial, and you have to resort to uncertainty and probability. So one of my favorite examples is, हाँ आप तो बड़े आदमी हैं, positive sentiment. हाँ आप तो बड़े आदमी हैं, not positive sentiment, right? So this is called illocutionary sarcasm. Illocutionary sarcasm depends on the body language. So that's why multimodal AI has to be used. Okay. So how is the training data prepared? You see, this sentence, I like the storyline of the movie. So I have sentence A, B, and C. This is how the training data looks. Okay. So in the lab, you will be given training data for training a backpropagation system. And the data will be given in this form. Here I'm calling it sentence. You can call it instance A. And positive, negative, and neutral are the 3 classes. You can call this C1, C2, and C3. So instance A belongs to class number 1. And therefore it has a 1 here, 2 zeros on the other 2 classes. Instance B, 0, 1, 0. Instance C, 0, 0, 1. This is how the training data is given. Now, since you will be using softmax or sigmoid, you can see that these levels can never be reached by the learning machine because these values can be reached only at infinity. for sigmoid, the value can become only when the input is infinity and 0 when the value is minus infinity. These values cannot be reached, but you should be able to go as close as possible. So as close as possible is decided by the cross entropy function, the distance between the target and what is obtained. So input and output are given. The difference between the target and the obtained value is called the loss function. So there are two popular loss functions. One is total sum square loss. This is a very general loss function, but total sum square loss function suffers from underflow. Okay, because it squares the difference between target and output in case of very small values. The output is the difference is small. When you square it, it becomes still smaller. And cross entropy is popular because most of the time in AI, we have to deal with probabilistic situations. So cross entropy is a measure which finds out the distance between two probability distributions. So softmax and cross entropy go very well together. These two are generally put together to train a learning machine. So this is how the cross entropy looks. HPQ. Q is the observed distribution. P is the target distribution. P, for example, would be 1, 0, 0, 0, 0, 1, 0, 1, 0, etc. Q would be the output of sigmoid or softmax, which gives a observed probability distribution. So cross entropy is defined in the following way: sigma minus sigma x equal to 1 to n, k equal to 1 to c, p x comma k log 2 q x comma k. What is this? X varies of n data over n data instances. C varies over the classes. So if it is positive, negative, neutral, sentiment, then there are three classes. So k is from 1 to 3. 1 for positive, 2 for negative, 3 for neutral. And X varies over how many such sentences you have given, marked with 1, 0, 0, 0, 1, 0, etc. And P is the target distribution. See that P x comma k and Q x comma k. This is the cross entropy definition. Target distribution, log of observed distribution, summed over classes, summed over data instances. Okay, so this is how cross entropy is defined. And total sum square error you have already seen. T minus O square, summed over classes, summed over data instances, multiplied by half. Okay, cross entropy loss. Can we sum up the cross entropies over the instances? Is it allowed? Yes, summing up cross entropies is equivalent to multiplying the probabilities. Minimizing total cross entropy loss is equivalent to maximizing the likelihood of observed data. So maximum likelihood principle you have done in your, I think, probability and data interpretation class. I believe I took a part of your class last semester or last year, maybe. Yeah, after midsem I took the classes. So maximum likelihood is based on setting the parameters such that the probability of the observation is maximized. A very nice principle. So how to minimize the loss? We apply gradient descent approach, backpropagation algorithm. Involves derivative of the input-output function for each neuron. And feed-forward network with backpropagation is the most important technique for us in this course, okay? Because this is the neural network-based AI we are discussing. The sigmoid neuron looks like this, only one neuron. Softmax neurons look like this. So I'm omitting the hidden layer. We have the input vector here, x0, x1 up to xm. The I superscript is for the ith instance. And the outputs are O1, O2 up to O capital C, where the number of classes is C, 1, 2, 3 up to C. And a very important quantity is the net arriving at every neuron. Net 1, net 2, net C minus 1, net C. And the ith superscript is for the ith data instance. So OIC is softmax net IC, which is equal to e to the power net IC divided by summation over all the neurons, e to the power net IK, k equal to 1 to capital C. Okay, so this is how the output is obtained given the input. The inputs give rise to net, nets give rise to output. Through what function? Through the softmax function. So you can see that the softmax function is inherently nonlinear. Okay, so nonlinearity introduced, and we will show at some point of time that if the neurons are linear, then the hidden layer neurons do not bring any additional power. Okay, that we'll show later. Okay, we'll continue this discussion. Let me just discuss your quiz question. Okay, so most of you have done pretty well in the quiz. So the first question was, in a problem, the search graph is a complete binary tree of depth D. Okay, so S, then 2 children, then 4 children, then 8 children. Each node has exactly 2 children. Level 0 is the start node S. At depth D equal to 1, there are 2 nodes. And at depth D equal to 2, there are 4 nodes and so on. At depth D, there is the unique goal node G. So this means that there is a path from S to the goal node. Each arc in the search graph has cost 1. The search algorithm is a strange one. It maintains a closed list and open list. So it is general graph search algorithm applied to this complete binary tree. The search algorithm at any stage picks up a node for expansion randomly with uniform probability from the open list at that stage. Find the A, probability of success, and B, the probability of success without expanding any useless node. So most of you have got this correctly. So the first point is, I thought, a little tricky one because some of you have not got the answer right. The probability of success is exactly 1 here. Okay, so even though you are randomly picking up nodes from the open list with uniform probability, what will happen is that you have to remember the definition of success. The definition of success is that the goal node is picked up and transferred to closed list. This is the definition of success. The definition of failure is the open list is empty and the goal node has not been transferred. So that's why I ask you to give a lot of importance to definition. Okay, so the probability of success in this case is probability of picking up the goal node and transferring it to closed nodes. It has to happen. Okay, because if the open list node doesn't have a child, it will go to the closed list, reducing the size of the open list. So eventually you are bound to hit the goal node and transfer it to the closed list. This has to happen. Okay, and therefore the probability of success is 1. And this is happening because of the way the general graph search algorithm works. No useless expansion. So that means you pick up the exact node from the path from S to G at every step in the iteration. So what is the probability of that? The recurrence relation governing the number of nodes in the open list is ni plus 1 equal to ni plus 1. since one node goes into the closed list and two come into the open list. So in effect, you are adding one node to the open list. Therefore, ni plus 1 is equal to ni plus 1, where I is the depth of the tree and is also the iteration number of the search algorithm. Clearly, n0 equal to 1, n1 equal to 2, n2 equal to 3, n3 equal to 4, and so on. So you have to multiply the probability of picking up the correct node, the node on the path to the goal node. So that is uniform probability 1 by the number of nodes in the open list at this point of time. Okay. Now, is it obvious that you have to multiply these probabilities? Not so obvious. Not so obvious. Okay. What is at play here is a joint probability and some independence assumptions. Okay. The joint probability is probability of S, comma, probability of S, comma, the node in the path, comma, the node in the path at depth 2, comma, the node in the path at depth 3, and so on. So you have a joint probability. You have to break it up by chain rule if you are rigorous and correct. Okay, but I have not deducted any mark for that. And then you have to apply independence assumption. What is the independence assumption? The probability of expanding a node is independent of the probability of expanding its ancestors except the immediate parent. This is called ancestor freeness assumption. Okay, so the probability of expanding a node in depth I, given the node, its parent was expanded at depth I minus 1, that is the only relevant probability. Okay, and that's uniform. Now, now this is how the probability comes out to be 1 by d plus 1 factorial. Any question on this?
The number of experiments done, right? Because every experiment will give two more that will take away one more. So,
what is the question?
What will be added on the number of experiments done instead?
Instead of depth. Ah, yes. Oh, okay. Okay. I mean, you're saying that it is not DFS or anything, just not DFS. So just consider the. So in that way also, do you get the same answer? Yeah. Okay. So next question is, that was a tricky one and a very, very difficult one. In a problem, no, sorry. An A-star algorithm runs with a heuristic that satisfies monotone restriction. H parent less than or equal to cost of parent child plus H of child. At a stage of search, the open list contains two nodes N and M. This is a very, very special, this is a special case. Okay, both N and M are in the open list. It is not the case that M is appearing later in future. That would be a more difficult case. N is expanded and is moved to the closed list. After some time, M is expanded. M regenerates N. So N is a child of M from the search graph. Prove from first principles that the parent pointer of N need not be changed to M. You are not allowed to use the monotone restriction theorem that under MR, any expanded node has already found the optimal path from the start node to from the start node S. Okay, a very special case is this, that M is expanded immediately after M. Even that has subtlety. And you get full marks if you do this very special case. Okay, with a bit of liberal evaluation this time. Since N was expanded before M, Fn must be less than or equal to F. That is by the property of A star. So Gn plus Hn must be less than or equal to Gm plus Hm. Also, by monotone restriction, since n is a child of m, hm must be less than or equal to hn plus cm comma n. Now, if you use these two inequalities, then if you add them up, then gn comes out to be less than or equal to gm plus cmn. Okay, and hence not necessary, not necessary to redirect the parent pointer of n. There is a big caveat here. What is the caveat? That when m is expanded, when m is expanded, one of the sorry. So, okay, so m and n are in the open list. Now, when n is expanded, okay, it may change one of the ancestors of m. Possible? So you see, we are comparing gn and gm, assuming that when n was, what is the snapshot? When n is expanded, we compared fn and fm and found that fn is less than or equal to fm, which is gn plus hn is less than or equal to gm plus hm. At that point of time. But the moment n is expanded, who said that gm will remain the same? It is possible that m is changing one of n is changing one of the ancestors of m. Okay, one of the children of n is an ancestor of m. Then what happens? Then also the proof needs a little more steps. Okay, then what will happen is that the path of m to s will change and it will pass through n. Okay, and so the path of m will have the path from s to n as a prefix. Okay, in that case, the cost of gm, the value of the value gm cannot be less than gn. Okay, if the path of m to s has a part passing through n, then how can gn be more than gm? Okay, so this is one subtlety which requires to be considered. And if you think that m is not expanded immediately after n, there are intermediate expansions which can change g values, then it becomes immensely difficult. Okay, but I have not considered that. I just wanted to say that these two basic inequalities you can apply, and in a very special simple case, you can derive this condition and prove that m's parent pointer need not be redirected. The general proof is as given in the class or in the book. The class's proof, which is there in the slides, is little more elaborate, considers a number of special cases of this. Okay. But this is the case. Okay. So fine, we'll continue. And in the lab, remember that you will have to implement sigmoid with the sigmoid expression for weight change will be derived tomorrow.